it's never a bad idea to lock your cross slide on an operation so that you don't, hypothetically, bump the hand wheel and bork the setup that you've just spent a whole bunch of time creating. Hello Internet, my name is Quentin and this is Blondihacks. I'm back on the Pennsylvania A3 switcher locomotive build today, and it's a banner day on this project so far because we're going to finish the boiler shell. This is a pretty big milestone in the construction of this boiler, so we've got a lot of fittings and fixtures to make, and we got a lot of silver soldering to do, some of which is good and some of which is adequate. Let's go. Here's where we left off. We've got a fancy looking cylinder with some fancy looking holes in it. Now it's time to fill all those holes with equally fancy, hopefully, bushings and such. So let's get going on that. We've got a lot of bronze parts to make here. First up are the handrail studs. We need 4 of these, so I've got a small diameter piece of bronze round bar here that I'll chuck up in the lathe, and I'm going to face that off as is tradition. Most of the parts that we're making here are these little blind threaded studs that just allow you to mount things like handrails and other accessories to the boiler shell itself because it's a convenient place to mount things. The main trick to these is to get just the right number of threads on the end. You may recall that the mounting holes for these studs are threaded in the shell, not for structural reasons, but just for silver soldering fixturing. The shell is very thin, so we need just enough threads to thread into the shell without having the bushing stick through the shell. This is a 40 TPI thread, so the math says for an 80 thou thick shell, that should be about 3 threads, not accounting for the curve, of course. Next, a little bit of action with the center drill and the tapping drill for the threads that will be in there. I'm measuring all these depths with the quill hand wheel markings, which is more accurate than a Sharpie mark on the drill, but less accurate than setting up an indicator on the quill, but certainly accurate enough for these parts. And I'm also going to go in a little bit with a larger drill. The drawing specifies a counter bore in the ends of these little studs. Presumably that's to make sure that whatever threads in these will sit tightly down on the surface of them. Now I can go in and tap that hole. These are 348 threads, which is pretty small. Not the smallest on this engine, but pretty small. However, this is bronze, so we don't have to worry too much about breaking taps because this stuff taps super easily. These are blind holes that are fairly shallow, so I went ahead and bottom tapped them as well. When starting the bottoming tap, I always counter turn it a little bit like so, and you can feel it when it finds the thread and drops in, and then start turning it. Especially with these really fine and small threads, that ensures that the bottoming tap doesn't get cross-threaded in there and mangle everything. It's not likely, but it can happen. Now I'm ready to part this off, so I've got my parting blade in there, and I'm just finding the edge of the part with my scale there. I'm sweeping the scale back and forth across the front of the part until I feel it start to drag on the parting blade there. And then I can zero the DRO and pan over from here to get my length, or you could set a dial indicator on the carriage at this point to get the length. I find this method to be accurate within about 0.003 for getting the length on a part. If you need more accuracy than that, then just part it off long and flip it around and face it down. Of course, always break the edge while I can. And Yahtzee. After a little cleanup and deburring, here's the final stud here. Now I need 3 more of them, but before I make those, I want to test fit it on the shell here to make sure I got the number of threads correct. The drawing shows them being perfectly flush with the shell when they're installed, and I don't know how important that is, but I'm guessing it's at least fairly important. So I threaded that in there, and that actually looks really good. It's a little bit proud of the surface just because it's a shell that's round, and you'd have to file the bushing round to get it to be perfectly flush, but I'd rather they be a teeny bit proud so I can file them down later if necessary. I'm really happy with that fit, so I went ahead and made 3 more exactly the same way. And let's get those installed, see how it looks. That looks really nice, I'm pleased with that. You can imagine a handrail mounted there someday. We need 1 more of those studs at the front here, which is the same except for some different threads on it, and this one is my favorite because it's the bell stud. Someday there will be an adorable, tiny little bell mounted here. Every locomotive needs a bell and a whistle, and I'm looking forward to installing the bell on that stud someday. Rather than show you making a bunch more bushings like that, I'm going to take this opportunity to show you a cool DRO method for the lathe for mass producing parts. This is something that my friends and colleagues who've had DROs on their lathes longer than me have showed me, so I want to share it with you. I start by facing off the end of the stock and then zero the Z-axis on the DRO right here because we know the tool is right on the end of the part because it just created that surface. Then take a light cut down the diameter just to clean it up. We want a light cut here so as to avoid any deflection in the work or the tool. And then we take a good quality micrometer, preferably a 1/10 micrometer, and we measure this surface as accurately and carefully as we can. This step is important. Measure that right to the 1/10. I've got 405/10 here. So then I go over to the DRO on the x-axis and I punch in that value. Basically, we're telling the DRO where the end of that tool is now. It's at 405/10, right on the money. And of course, make sure you're on diameter mode. If you're on radius mode on your DRO, you're about to scrap the part. Ask me how I know. Now you can make a series of passes, heavy or light, whatever you like, and turn your part down. And when you get close to final diameter, you can just use the DRO and dial in the exact diameter that you want. In this case, I want 313, so I dial that in, make my finishing cut, and then let's see how we did. We get the micrometer on there. Survey says 313 and 1/10, right on the button. And if we look at the DRO, we see that in fact 313 and 1/10 is what the DRO said it should be. Now, to be clear, I got a little bit lucky here. You don't usually nail it quite to the 10th like that, but if you do all of those steps carefully, you should get within a few tenths of this every time. Now the power of this is that after doing that once, now we can produce all the subsequent parts just by running the machine to the numbers. So pull the stock out until it touches the tool at 0, move it a little past, face it down, now you're at 0 on length, then turn down to the diameter on the DRO, and you can crank down part after part without measuring anything. This also all requires that you don't touch your tool post angle and that you don't change the tool. If you want to change the tool for different operations without losing all of those positions, then you need to start learning about tool offsets in your DRO, and that's a much bigger topic that I'm not going to go into here. Back to the part now. This is one of the water inlets, and these parts are fully threaded with a hole down the middle, so they're very straightforward to make. Really the only tricky step is the parting off process. When parting off a fully threaded part like this, you really can't use a parting blade because the parting blade is just going to engage with that thread and deflect and wander off. So instead, I'm starting with a grooving tool here, which is at the end of the day just a short rigid parting blade, and I'm making a flat spot. Then if you needed to, you could switch to the parting blade at this point because you've got a flat spot so the blade won't deflect. However, this is a small part, so I can just do the whole parting job with the grooving tool. The grooving tool is a handy way to remove threads from an area if you need to. You could say that technique is groovy. Now I should be able to thread this into the boiler shell here. This is a fairly coarse thread, so there's only like half a thread or something in that shell, but it is just enough to thread that in there and hold it for silver soldering. Next up is one of the two large bushings that go on top. This is the water fill bushing. This is a very straightforward part here, so I'm not going to go into a lot of detail. I'll just let you have a little Zen machining time. If you're wondering why the water fill bushing isn't visible on the final model, it's because it's hidden under the sand dome. The sand dome on this model is not functional. I don't think the physics of falling sand scaled down this small very well, and I don't think sand is appreciated at Model Engineering Club tracks anyway, since the rails are mostly aluminum and it would probably just make a mess and wear out the rails. On North American locomotives, the sand is stored in a dome on top of the boiler like that because that helps keep it dry, which is very, very critical in a gravity-fed sanding system. Later locomotives, however, moved to using steam pressure for forcing sand out onto the tracks, and so this was a little less important. I'm just test fitting on the shell here before I pull the part down off the lathe and make sure I've got a good, easy sliding fit there. And that looks good. That needs to not be too tight so that the silver solder has somewhere to go. And there's one happy little water fill bushing. If I did my job right, that should slide right in there and be ready for silver soldering. And here's what all of that looks like on the inside. It's kind of neat seeing how everything sticks through there. Pretty soon we won't be able to see any of this anymore. If we do see all this again, it means we're having a real bad day. Next up is the great big hole next to that, and this is for the steam dome base. And this is a very important feature. At the time, I was not able to source a large enough piece of bronze round bar for this piece, so instead I bought this piece of flat bar for the job. It's got enough thickness here that I can get the disc I need out of it. I'm going to start by scribing an oversized circle here. This is going to be quite a bit larger than the final part to give myself some margin for error here on the subsequent steps. Then over to the bandsaw, and I'll rough out this shape here to reduce the amount of work we need to do on the lathe and to make for easier cutting. That's going to be important here, as you'll see here in a moment. This material is not really thick enough to hold onto in the chuck and still be able to turn the part, so I'm going to need another way to fixture it in the lathe. I'm going to use a method called pressure turning. It's a very old school way of turning thin disc parts like this. So I've got a piece of aluminum here in the lathe, and I'm going to face off that mysterious center that's in it from some previous operation. Give myself a nice square surface there. Then I'm going to start turning this down into a disc with a shoulder on the back of it. This is going to be a pressure pad. You've seen me do this before, and I have other pressure pads in my drawer, but I don't have one the exact size we need for this case, so I'm making another one. And to be clear, the shoulder is mostly decorative. It just looks nice. Next, I come in with a great big center drill, big by hobby standards anyway. I think this is a number 4, and I put a very generous center in that, and that's going to be for tail support on the pressure turning operation. Now I'm ready to part this off. For a little extra grip on the pressure pad, this is something I like to do. I got the spray glue here, ye old Super 77, and I will spray that away from camera and face onto a gloved hand because this stuff gets everywhere and makes a terrible mess of everything it touches. There's a little glue on there, and then I'll glue some 320 grit emery to my little pad here. Once that glue is set, then I can just cut around that with a craft knife here. And tear that edge clean, and presto, one adorable little pressure pad. These little pads only take a moment to make, and then when you're done, you just throw it in the drawer, and someday when you need another one that size, you've already got it. Now for the mating surface, I still had the stock in the lathe for making the pressure pad, so I just faced it off in situ, and now I've got a square mating surface. I also grabbed anything that was pointy out of the lathe tool drawer and just put some concentric face rings on here. That'll help the super glue adhere, give it a little bit of traction there. A little bit of isopropyl alcohol there will clean up the surface, make sure that super glue has a good hold. I mentioned that pressure turning is a very traditional technique. Super glue, however, is not. But super glue makes a great addition to this technique. It just helps really ensure that the part is not going to go anywhere. You could also put emery paper on this side as well if you wanted. But the nice thing about super glue is that sometimes it's enough by itself, and you'll see me take advantage of that here shortly. Now I'm going to bring in the pressure pad, and I'm going to hold it in place with the tailstock there. And I'm just arranging the part so that visually the scribed circle there is centered on the pressure pad. The goal is to make sure I've got enough material to turn down there and hit my dimension with everything cleaning up properly. I leave that sit with some pressure on it so the glue will cure, and now we're ready to turn. You'll see some wobble in the pressure pad there, and that's because being rolled plate stock, the sides of it here are not particularly parallel. But that's okay, it's still going to work just fine for what we need here. Initially, of course, it's a very interrupted cut, but quickly enough we get into full material here after the saw cut is gone, and we can start turning to dimension. With that side done, now I can remove the pressure pad, and I want to face this front surface here. I'm doing this with very light cuts since I'm now relying only on the super glue, but that's okay, we can get it done this way. This is important because it's now created a surface that's square to the sides that we turned, even though of course that flat bar, as I said, is not parallel on either side. So with that square surface created, now I can bring the pressure pad back in, and you'll note that it's running true now because that surface that we just created is square to the tailstock, and I can turn the shoulder that we're going to need on this part. This is the registration shoulder that actually slides into the boiler shell. Every time I make a disc-shaped part like this from flat bar, people always ask why didn't I trepan it. I know everyone's really excited about that operation, it's an interesting one, but it doesn't scale down very well on smaller parts like this. The tool geometry that you have to create to do that has no strength because of the sharp radius that you have to create underneath the cutting edge. There's lots of operations like that that you see the big kids do that just don't scale down very well to model scale parts like this. Once again, the fit is important for a good silver solder joint here, so I'm test fitting on the shell before I take it down. And in this case, it needed a little bit more. I took another 1 thou finishing cut there just to get a good sliding fit there. We've done what we can with the super glue mandrel now. Sometimes you can just tap the part right off of there, and sometimes they're a little better stuck than that and you need a little bit of heat. Heat is pretty much the universal glue killer, so after a little bit of that, now the part understands that I was serious about that tapping. Now I want to face the other side of the part parallel and bring it down to final dimension. So for that I'm going to use the 4-jaw here because I've got enough meat on this part now that I can hold it this way. The only trick here is getting it sitting parallel in the jaws to the face that we've created there. So for that I've got an adjustable parallel here, and I expand it to meet the part underneath, and then I tap the part firmly down onto that parallel. That does a pretty good job of getting it square to the chuck face, at least good enough for this application. Then finally I can dial the part in, and then after that I go back and check it with the parallel again. Usually you have to go back and forth a couple times between the parallel and the indicator before you get it running true and square, because each operation tends to cause the other one to move a little bit. Now that looks to be running very well, so now we can get on with the facing operation. And here we can take fairly heavy cuts because this is a good grip here. For checking my dimension here, I've got a trick tool that was sent to me by a viewer. It's a low-profile stare micrometer. The anvil on that is actually replaceable. You can change it out for different things, but the default here is a nice flat one that allows me to get in behind parts on the 4-jaw like that. And if you want to see how you're doing on parallelism, you can check the thickness in a few different places. And in fact, you can adjust your cut if you do this before you're finished, and then tap in the high spots to get it really parallel. This is a technique that I demonstrated in my video about making a chuck backing plate for the rotary table. Over to the mill now. I'm going to set it up to put a bunch of holes in it. I need to get the spindle centered on this part, so for that I'm going to use my spindle indicator holder here. I've got a video on making this if you're interested. The nice thing about this versus something like a coaxial is that you can indicate in a partial curve, as I'm doing here, because I need to work around the clamps. This is quite easy to do. Once the front curve is dialed in, I can check the back, and if you did it right, then the back shouldn't even need any adjusting, which it does not. Another way to do this would have been to put a center in there while it was still in the lathe, and then use that center with a pointer in the spindle to indicate it here on the mill, but I didn't want a center dimple in the middle of this part just for cosmetic and pride reasons, I guess. So we drill a whole bunch of holes in that, most of which are for admitting steam from the boiler into the steam dome, one of which is for the steam pipe that goes back down into the boiler, and then the 4 holes in the corner are blind threaded holes for mounting the steam dome. One other little trick feature here is that the steam pipe hole needs to be counterbored on the back for the steam pipe to be recessed into. So for that I've got the part flipped over and I locate that hole using the drill inverted that was used to create it. This is kind of a cheap and dirty way to locate a hole. It's good enough accuracy-wise for this operation. And then I'm using an end mill to get a reasonably flat-bottomed counterbore in there for the pipe to seat into. Conveniently, the diameter of the pipe is the same as an end mill. There is the completed steam dome base. So that is now ready to go on the boiler. Next, we need to make the pipe that connects to the underside of that base and routes the steam to the front of the boiler where it can be sent down into the cylinders. That's a little bit of a trick here. I've got a piece of pipe from McMaster for this, and I'm going to mark it out for bending here. This pipe goes down from the steam dome base and then towards the front of the boiler, and then also needs a little bit of a dog leg in it to get to one side of the front tube sheet. And here is where I learned, as this pipe cracked and twisted, that this straight tubing from McMaster ships in the half-hard state, not the annealed state that copper tubing normally comes in. So I had to cut off that failed attempt, and I went ahead and annealed it and did that bend a second time, and that worked beautifully. The purpose of this pipe is that steam is collected in the steam dome at the top of the boiler. That's basically a primitive form of drying out the steam, because only the hottest steam will rise up into the dome. And then the steam goes into the dome and back down through this pipe, which runs back through the boiler, continuing to heat the steam a little bit more and dry it out a little bit more before being fed down into the cylinders. A bunch more fiddling and test fitting and trimming and bending later, and I had my little 90-degree dogleg pipe here that feeds from the steam dome forward to the front tube sheet. There's also a little fitting that goes on the front of that pipe that I made off camera. It's not very exciting. Someday that will get soldered into the tube sheet on final assembly, but that's a ways in the future yet. So everything is looking good. You can see how that pipe is routed there. It's kind of a poor man's superheater. This boiler doesn't actually have a superheater on it, but that routing of that pipe does help dry out the steam a little bit, I'm sure. Okay, time to break everything down and start silver soldering. These parts are all getting silver soldered one by one. It might be tempting to try to do them all at once or in groups, but that is not a good idea, as Kozo reinforces in his book over and over again for many reasons. So I've got everything fluxed, and I got some silver solder on there, and I've got everything insulated as best I can to help keep in the heat. This really helps the silver soldering go better in my experience. And away we go. As always, whenever possible, I heat the joint from the far side with the solder sitting on the near side, and using the patented Kozo scratch rod to keep things organized and help the solder flow everywhere that it needs to. This is the first of the handrail studs. Once that solder is flowed, then you let it cool down and then pickle everything, clean it up, inspect the joint, move on to the next one. You do them one at a time like that. It really is the best way to ensure good joints on everything. And that went really well. I've got a nice clean soldered ring around the top and an overly generous blobby fillet on the bottom because, as always, I used too much solder, as I tend to do. Literally rinse, repeat, and do all the subsequent bushings the same way. All the studs and water inlets and stuff are all quite straightforward. But now things get a little interesting. The water fill bushing is slightly tricky because it's sitting on top of a convex surface, and that means it's difficult to keep the flux and the solder from running off. But this bushing needs to be soldered in this position because it's not threaded in like all the others, so it would be difficult to keep it straight and square if you were trying to solder it from below like I was doing the other ones. But this one went fine, again, using the scratch rod to make sure the solder goes into the bushing and not just running down the sides everywhere. Although, of course, a lot of it does run down the sides because, once again, I used a little too much. But that joint is certainly sound. I got a nice ring of solder through the bottom of it, so everything looks good there. Over to the surface plate now, because things are going to get interesting with the steam dome base. The key challenge with this base is to make sure that it ends up level. Now, Kozo has a very elaborate procedure for this, involving putting little pins above and below the shell and filing little notches into the shell to make sure that the steam dome base sits perfectly square. I think this procedure makes sense if, as he suggests in the book, you've created that hole by fret sawing and filing and hand fitting it. It's going to be a bit of a loose fit then, and the steam dome base is going to tend to sit crooked if you're not careful. And it might move under silver soldering because everything moves while you're silver soldering it if it's not really well secured. However, I made that hole in the shell with the boring head, so it's extremely round and extremely accurate. I've got a nice close fit on the steam dome base as well, so there really isn't enough clearance in my case for the base to get crooked. So I don't think I need this whole procedure. But just to be sure, I'm going to set it up on the surface plate the way he suggests and check it for level. This involves lining up the scribe lines that we put in that shell very early on each side at the same height. So it's basically using the height gauge to find the height of one line and then adjusting the rotation of the boiler until you find a position where both lines are on the height gauge on both sides at the same time. Then you know you've got the boiler shell sitting horizontal, and then I can put the steam dome base in place there. Then just by carefully sweeping the height gauge across the top of the steam dome base here, I can tell that it's sitting extremely square. You could get out a long straight edge and start taking measurements on each side and so on, but that's really not necessary. I can just see from the way that the scriber floats over the surface here that the steam dome base is sitting very, very flat there in the position where it naturally wants to sit. And again, there really isn't enough clearance for it to rock side to side appreciably. So I think I'm going to forego Kozo's method there and I'm just going to go straight to the next step, which is to solder the pipe into the steam dome base. I've marked some scribe lines on there for the alignment of the two, so I make sure I get them correct. And since these are small parts, I'm using the small torch, and I'm just feeding the solder in by hand once things are hot, because that's just easier for tiny little parts like this. The main reason I wanted to avoid Kozo's pin method for the base, if I could, was that it's going to make the joint much more complex. And I know from experience that these steam dome bases and similar parts are already very difficult to solder well, and I didn't want to make it any more difficult than necessary. But now is the time to do just that, so I've got everything fluxed up here, and let's get everything seated together and start soldering this thing in. The challenge with this joint is that unlike all the others, we can't heat it from the far side. That's by far the best way to ensure a good silver solder joint. However, we can't do that here because we would overheat that delicate little steam pipe that's mounted now on the underside of the base. So we have to form this joint entirely by heating it from above. The best we can do is try to focus our heat on the shell around the steam dome base there to try to make sure that it's the heat of the joint itself that's pulling the solder in and not the torch flame melting the solder directly. That's what we're trying to avoid here. So we've got a complex joint here and a very less than ideal soldering technique, so it's going to be challenging to get a good joint here. I did the best I could though, and once again using the scratch rod to try and encourage the solder to go down into the joint rather than rolling off the sides. And once again, I used way too much solder here, even more than usual this time because I was super paranoid about not getting enough down into that complex joint. The more complex the geometry of the joint, the more solder it will consume to get a good fillet and a good seam of solder all the way down through it. After pickling and some cleanup, here's the final result. It is certainly not pretty. Obviously I used way too much solder and a bunch of it ran off the sides, and the stuff that ran down kind of got a little globby because there wasn't enough heat down the sides to flow it. But I do see a fillet all around the top, and I think I see a line of solder all the way through around the bottom. It's hard to see in there and be sure, but there's definitely a nice fillet all the way around the outside of that joint, so I feel pretty good about its mechanical integrity, even if it's not going to win any beauty contests. I can clean up some of that overrun solder later if it passes the tests and is worth keeping. And since someone always asks, no, you can't just reheat it and flow it again to improve the situation or make the joints look better. Silver solder changes its chemical composition once it's melted the first time. The melting point goes up enormously. That's kind of the whole point of it. In order to remelt silver solder, you'd have to get it so hot that you'd melt the copper and the bronze parts around it. Just because it has the word solder in it doesn't mean it behaves the way that the solders that you're used to do. I'll do one more check on the surface plate here to make sure that the steam dome stayed level, and indeed it appears to have done so. I can't find any evidence that there's anything crooked about that steam dome base at all, which means that the steam dome bolted to the top of it should be straight. It looks good. So I'm sure people will have plenty of opinions about how that steam dome base joint went. However, none of this is visible in the end. It's all covered by lagging, so I don't care very much what it looks like. I care if it's mechanically sound and if it's going to pass a pressure test. We're going to find out here hopefully soon, because my intent is to pressure test the shell here by itself and find out if the joints that I have so far are good while I still have access to the backs of them before final assembly of the boiler. Fixing these joints at the end is extremely difficult, as you know if you've seen my vertical boiler building series, so it's very important to fix them now if we can. But that's where we're at so far. The boiler is starting to take shape here. I'm feeling pretty good about how things are going. Lots more work to do though, and more difficult joints to come, so stay tuned for all of that. Thank you to my patrons for making all of this content possible, and thank you for watching, and I will see you next time. Is that your microphone now? No, that's it. This isn't helpful. I know you think you're helping, but you're really